Like the previous examples, I could do this in the playground. And of course, the playground has a lot of advantages. For example, you don't need to install anything. You just open the playground in your browser and you can immediately start developing Marlowe contracts and then also immediately send them to the simulator and try them out. So that is really nice. However, I want to show you an alternative that I personally prefer, namely how to write Marlowe contracts locally. We have a GitHub repository accompanying the course. It's input output -HK Marlowe Pioneer program. We'll put the link in Canvas. And at the moment, there are just some code examples in there. So the ones I showed you at the beginning of this lecture from last week, but now in Haskell. And this double pay and double pay refactored is what we just looked at in Haskell, how to refactor this example contract and make it much shorter and nicer. And finally, there's this multi-pay that I now want to show you. So if you clone this repo and then change to the folder in your terminal, then you can cd into the code folder and do a cabal build to build all the example programs. In my case, I've already done that. If you do it the first time, it will take quite a while because there are a lot of dependencies. So the advantage of doing it like that is that you in particular now have all the normal Haskell tools available at your disposal. I mean, one thing you can do is you can actually run one of those programs. So for example, there is simple payment pay. That was the very first example we looked at, where just one party deposits money, which then gets paid to another party. And if we execute it, what I told you before, that all these Haskell programs do is they print the JSON version of the Marlowe contract to the screen. So you can see that here in action. So that's, of course, not very interesting. So why I particularly like developing locally is because now you have the REPL, the Haskell REPL available. So if I do a cabal REPL exe simple payment pay, I end up in a REPL and now I have the usual interactive tools available. So for example, I can ask for information for the type contract, the type of Marlowe contracts, and then I get all the constructors, close, pay, if, when, let, assert. So I want to show you how to implement this multi-pay contract where the number of givers is arbitrary in Haskell, doing it locally. But again, you could just as well do it in the playground. I just wanted to show you an alternative way of developing Marlowe programs in Haskell. Of course, it's also possible to run a local version of the playground, but I'm not going to show that in this lecture. I already wrote the code, so I don't want to spend too much time on that because this is, after all, a Marlowe lecture and not a Haskell lecture. And most of you are probably not familiar with Haskell anyway. So the main point I want to get across is that by using a programming language to emit Marlowe code instead of typing in the Marlowe code either directly or in Blockly, offers the advantage that by doing that, you can have something like templates that are much more flexible than what you can achieve in Marlowe by using parameters for values or times. It's already nice that we have these parameters, but if you want variability in the structure of the contract itself, then you need more powerful tools. And you can achieve that by using a program that generates your Marlowe contract for you. So that's the main point. And again, you don't need to use Haskell. You can use your favorite programming language. And if you're not a programmer, you can also, of course, always write Marlowe directly. So this is more for power users. So let's start a REPL for this example. So that's called multipay. And let's also look at the code. So this is the normal structure of a Marlowe program. Here's the main program, and this is the interesting function. So contract now, before we had three parties, giver one, giver two, and the receiver, and then the deposit value and the timeout, the deadline. So now I replace the two givers with a list of parties. So the idea is it can be arbitrarily many givers, and this should produce an appropriate Marlowe contract then for an arbitrary number. So I can demonstrate it if I call cabal run on multipay now. This will be a contract for three givers. If I change this here and in the main program remove giver 3 and run it again, we'll have to recompile, but that should be fast. And now this should be the original contract, the example we looked at in the previous section. They can also go crazy and add two more givers. The names, of course, are arbitrary. Don't have to call them giver 1, 2, 3, 4, 5. Now we see the contract is really, really long. So that's what I mean by structurally different. So by using this Haskell program that generates a Marlowe contract, we can, by simply changing some parameters, generate really different Marlowe contracts that are structurally different. So this one here for 5 is much longer, because for 5 deposits, you have 120 possibilities in which order they make their deposits. So let's look at the code. So the interesting function is this contract function. And what's the idea? So in principle, there are two parts. First, we have to wait for all the deposits. And once all the deposits have been made, each of the internal accounts that now contains an individual deposit has to send the money to the receiver. And for this first part, what we need at the top level is a when contract, and then we need cases for all possibilities. So for a list of givers, what are the possibilities? Well, each giver in the list could be the one that makes the first deposit. So what we need is, given a list of givers, we must somehow produce a list of possible first givers and the rest. And that's why I wrote the helper function here. So that's one of the nice things of using a programming language to generate your Marlowe code for you, that you, for example, can have these helper functions. We saw those before, like this deposit in the previous example. So this is the same actually, but it can also be like general purpose helper functions that are not local to the function you're writing, but you could even put that in the library. You could even imagine assembling a little library of useful utilities for generating Marlowe programs. So this picks function, just very briefly, giving a list, it produces a list of pairs of one element in the list and the other elements. So we can try that out in the REPL now. That's so nice about doing it locally. So I can just do picks and now give an arbitrary list. Let's say a list of integers. So let's say 1, 2, 3, 4. And just to make Haskell happy and unambiguous, let's say that it's of type int, doesn't matter. And that will give me this list of 4 elements. So given these 4 numbers, I could start with 1, and these are the rest, 2 through 4, or 2 could be the first, and then 1, 3, 4, others 3, 1 to 4, and 4, 1 to 3, and so on. And of course, I can have more elements, and then there are accordingly more possibilities. So that's this helper function I wrote here, and I'm using that now. So on the top level, I call this helper function go, initially with all givers. And now there are two cases. First case is that the list is empty. So there is no giver left. So all of them have made their deposits, or there were no givers to begin with. So in that case, I go to the second part where the payments happen. But if there is at least one giver left, then, so this is Haskell list comprehension. So I loop over these picks. Picks prime is just where I call my helper function. So now I have these possibilities with which giver to start and all the remaining ones. And now I just construct a case where the action is that the one that starts deposits. This is our old deposit helper function. And then recursively, I continue with the rest. So for example, for 3 givers, this picks would be, I mean, we can try it out. A 3-element list, which tells me, okay, in the case of 3 givers, giver 1 could start and 2 and 3 are remaining. Giver 2 could start and 1 and 3 are remaining, or giver 3 could start and 1 and 2 are remaining. So in this outermost loop, I would construct a when with 3 cases. And the 3 cases are 1 makes a deposit, 2 makes a deposit, 3 makes a deposit. And then in that case, the continuation now recursively calls go with the remaining ones. So I have givers 2 and 3 left in this case. So now again, there are 2 possibilities that 2 makes the next deposit or 3 and so on. In the last case where 3 starts, the remaining ones are 2 and 3. And there are also 2 cases that the next deposit comes from 1 or from 2. Okay, and this will take care recursively of all the necessary deposits. And finally, we call this payments function, which again gets the full list of all givers. And this payments, again, a recursive function. This argument denotes the givers that haven't paid yet. So if that's the empty list, if everybody has paid, we are done and we close the contract. And if there is at least one giver left, we make a payment from this giver to the external wallet of the receiver about the amount in ADA, and then recursively do the payments for the remaining givers. Let me paste this here into the playground so I can send it to the simulator. So now for 5 givers, I compile. If I look at the generated code, that should be really large. Indeed it is. So the resulting Marlowe contract has 6,699 lines. So that would be a lot of work to type that by hand. Send it to the simulator. And let's again pick 100 ADA. And let's see. So at the beginning, I have 5 possible actions. Each of the 5 givers can make a deposit. Let's say giver 3 starts. So now there are 4 actions left for the remaining givers. Let's say next one, giver 5 makes a deposit, and so on. Let's say 1, 4, and 2. And now the payments happen and all 5 givers pay to the receiver. So it seems to work. Of course, in order to test this exhaustively, I would have to try all 120 cases. And there are even more cases because some of the givers could refuse to make their deposit, in which case all the givers should get their money back. So again, the point is that by using a programming language, you suddenly have the power to write programs that write Marlowe contracts. So this is what this Haskell program is. It's a program to write programs. So this contract function is a function that produces Marlowe contracts. And as you can see, with relatively simple Haskell code, I can write vastly complex Marlowe contracts, a Marlowe contract with more than 6,000 lines of Marlowe code. So that's the power you gain by not writing your Marlowe contracts directly, but instead using a program that writes the Marlowe contracts for you. And again, don't worry about me using Haskell. You can use your favorite programming language for this. And also, if you are not a programmer, you don't have to worry. Just writing Marlowe by hand or using Blockly will already get you very far.